Very good afternoon, all students. Welcome to the class. Probably this is going to be the final class for this semester. And we have discussed all main issues. And last class, yesterday's class, we have discussed some of the important discussions about the sparse matrix, linked list-based sparse matrix, and time complexity analysis with a better understanding. So I'm sure those lectures were some more interesting and somewhat different than what we have discussed in earlier initial lectures. So time complexity, better clarity and definition and better understanding you must have developed by now with these discussions. Yesterday we have just done that. So today is going to be my final lecture for this semester on data structures. And today what we are going to see is another important data structure which we have not discussed till now. Till now what we have discussed is your arrays. We started with talking with arrays and their operations. Then we talked of a stack. We talked of a queue. We talked of a linked list. Then we came to trees and binary trees. And these we have discussed in more detail. And of course, we primarily consider this side as a linear data structures, as sometimes back also I said, and trees is considered as a non-linear data structure. In the non-linear category, there is another data structure also, which is called as a graph. So in this semester, you don't have detailed programming on the graph, etc. And in next semester, of course, you will study graph in more detail. But I will discuss with today graph data structures and its overview. So primarily, graph is another non-linear data structure like binary trees or trees, and it has its own lot of applications. For example, the most famous application you are well aware is Google Map. You are using Google Map and effectively you are able to travel without difficulty, without knowing any maps of any area, and Google Map helps you in driving in a big way. Effectively, if you see Google Map, what does it store? It has information about all cities and their. So there was some connection problem. I am reeling, so I am resuming there. So we were talking of a Google Map, and I say effectively Google Map has all cities and their connectivity being stored, and connectivity in terms of road as well as metro and even walking distance are all considered. But let's say we talk of cities and road connectivity for the time being, for the driving purposes. What effectively now it has internally, everything stored is a certain graphs. Like it has got various cities as vertex or vertices and roads as edges. For example, I say I have New Delhi. So from Delhi, I have a connectivity, let's say to Calcutta. I have a connectivity to, let's say, Mumbai. I have connectivity to Bhopal. Say I have a direct road from Delhi to Hyderabad. Let's say from here I have a connectivity to Chennai. So all these roads and their information available. Google Map maybe tells you certain connectivity like this also. Maybe similarly, this side I have, let's say, Chandigarh and many more like that. So similarly for all other cities also, there could be different connectivities. Now, you say you go with the shortest distance or shortest time. Effectively, Google Map tells you the path shortest time based, and you are able to travel that. That means it knows how much time is stored. So that time is also stored over the graph's information. For example, it could say from Delhi to Kolkata going will take, let's say, approximately 20 hours. So it could say, let's say, 1200 minutes. Delhi to Hyderabad, let's say it takes 1300 minutes. Delhi to Mumbai, let's say it takes 950 minutes. Delhi to Chandigarh, let's say it takes 250 minutes. And like that. So there is some information about each edge. So all that information is used and processing done. So processing, algos, logics used for all that. So graph has a variety of applications, and this is one of the fantastic application which is being used by everyone nowadays, almost very frequently after every few days. Not only that, so graphs have lots of other applications in computer science, like in operating system also graphs are used, in computer networks graphs are used, in cloud computing graphs are used, in distributed computing, and many more subjects like that, along with a lot of industrial applications also. Internet also, when you say internet you are using, or intranet you are using, LAN you are using, everything is effectively a graph. You have mathematically graph means what? Mathematically graph means it is nothing but it's a set of two sets. It is effectively G we normally call is as set of vertices and edges. So V we call as a set of vertices. And E we call as set of edges. So mathematically, these are considered to be unordered. So it doesn't matter in what order they are stored, sorting or nothing is referred. And of course, by default, they are unordered. But for certain applications, if I want, I could arrange them in certain specific ordering manner also. But mathematically, I mean, this is there. So generally, if I just talk of a graph, so we always say in terms of a data structure, we have to always talk in terms of their storage and some standard operations. So for graph also, we will understand the storage and some standard operations. But before that, graphs like this can be directed or undirected, meaning if the edges direction have, then they are said to have directed graph. Otherwise, they are undirected. For example, if I say Kolkata to Hyderabad is one-way connectivity only, you are allowed to go from Kolkata to Hyderabad. It's a one-way road only. In certain cities like Delhi, prerequisite. Again, there is some connectivity issue, I suppose. So let me just reconnect that. So now probably this is already again established. So if there is going to be some C programming being told, and once we have studied C programming only, then we can study data structure. Once we have studied data structure only, then we can study algorithms. Once we have studied only algorithms only, then let's say we can study CP. Once we have studied algorithms only, then we can study advanced data structure and algorithms. So all these decisions have some dependencies and they need directed edges. So in that case, your graph will be a directed graph. So this means that from C programming, we can go to data structures, but it doesn't mean vice versa. From data structure, I can go to algo subject, but not vice versa. So in this case, a direction is important, and hence why the corresponding graph is stored as the directed graphs. So direction is important, then we will store that information. Otherwise, it will be undirected graph also. So if I have a normal connection, this is both way or two directional, otherwise it will be one directional. So normal undirected connection means two directional, directed means one direction. So that is what is the directed versus undirected graph. Similarly, we have another category of the graph to be categorized as weighted graph or unweighted graph? Weighted graph will mean edges have weights. Like I have shown the corresponding time for the road travel. That was the weight assigned to this. So weighted graph means we store the properties of the edge. For example, I wanted the time, not only time, sometimes your distance. Maybe you want to travel with the shortest distance. So Google Map also stores the distance. Google Map also stores the time. Google Map also stores the toll tax to be paid. Google Map also stores some other variety of information, peak hours, the traffic, non-peak hours, etc., etc. So a lot of properties are there. All those effectively mean weight of the corresponding edge. So a graph can be weighted or unweighted. Unweighted graph will mean you have only a presence or non-present. So if an edge is present, then it has a weight or one weight, or otherwise if it is not present, present only. So you could say weight is not stored, its presence is only stored. So I can have a weighted directed graph. I can have a weighted undirected graph. Similarly, I can have unweighted, unweighted directed graph. And I can have unweighted undirected also. All permutations will be obviously possible. And all this needs to be stored in a proper manner into my algorithm for future processing. So as long as I talk of their storage, the graph needs to be stored either as an array or via linked list. So both storage are possible. And of course, then we will talk of operations. So array-based storage is called as adjacency matrix storage. And linked list-based storage is called as adjacency list storage. So there are two representations for graphs to be implemented. One we call as adjacency list, another we call as adjacency matrix. For understanding this, let's take a simple graph. We will be numbering the vertices with 0 to n minus 1 as mathematically or in programming we always use. So let's say I have lots of vertices 0, 1, 2, 3, 4, and there is some connectivity. Currently, I'm taking unweighted, undirected graph. Of course, later we will change it. So it is unweighted, undirected graph, and maybe I have something like this connection. And let's say this is 5. 0, 1, 2, 3, 4. So I say this has 5 vertices, and on 5 vertices, lots of edges are possible. So if I have to store it as an adjacency matrix, its adjacency matrix will mean I will have a 5 into 5 matrix. 2D matrix, obviously, 5 into 5 corresponding to every entry 1, 1, 2, 2, 1, 2, 1, 3, 1, etc., etc. So this is corresponding to row number 0, row number 1, row number 2, row number 3, row number 4. And this will be in column number 0 and column number 4. So this entry shows 0, 0. Effectively, if I have some connectivity like self-loop, then I will have on the diagonals corresponding values. If I consider self-loop, etc., in mathematically graph, we can have self-loop. So these entries can be 1 or it can be otherwise 0 because in case of a diagonals. Because that is not a connectivity among multiple different vertices. Diagonal entries refer to the same vertex being connected to itself or not, which is otherwise not applicable, but self-loop make a difference. 0 to 1. So this entry is a 0, 1. If it is present, yes. 0 to 2, this is connected, yes. So 1 means connected, and 0 to 4, 0 to 3, connected, yes. 0 to 4, not connected. So 0, 4 is not connected, and 0 to others, it is connected. These are all connected. Similarly, 1, 0, 1, 2, 1, 3, 1, 4, 2, 0, 2, 2, 2, 1, 2, 3, 2, 4, like that. If it is a weighted graph will have certain weights. Let's say 2 weight, 3 weight, 4 weight, 5 weight, 6 weight, minus 2 weight. Minus also weight could be somewhere meaningful. Although for Google Map, etc., minus weight, it doesn't make much difference. But for some other application, it will be. So like if I'm talking of total hours taken to travel, this could be available in this particular form. If the weights are stored, I will say 0, 1 has entry 2, 0, 2 has entry 5, 0, 3 has value 6, and so and so. 1, 0. 0, 1 connectivity also means 1, 0 connectivity. So this will also be 2. 1, so this is 0, 2, 4. 1 to 2. 1 to 2, there is a connectivity with 4. 1 to 3, there is no connectivity. 1 to 4, there is a connectivity with 3. I'll have this. Similarly, 2, 0, 2, 0, there is a connectivity with 5. Effectively, this and this value will be same. This and this being same if it is undirected graph. Of course, if it is directed graph, it won't happen like this. So I'll have all these entries 5, 0, then 2, 0, 2, 1. So 2, 1 means from this 2 to 1, we have a 4, effectively same as this. 2 to 3, I have minus 2. 2 to 4, I have 6. 2 to 4, I have 6, and 0 to 3. 0 to 3 was 5. So sorry, 0 to 2 was this. 0 to 3, 0 to 3, I had this 6 connectivity, and all this was okay. So this way it will be adjacency matrix. If it was a directed graph, for example, directed means I have a connectivity from node 0 to node 1 via weight 2, from node 1 to node 4, let's say 3, from 1 to 2, or 2 to 1 via 4, 0 to this could be 5, 3 to 0 could be, let's say, 7, and like that's it. For example, there could be no more connectivity. Then I will have an entries for the corresponding direction only. For the other direction, nothing will be stored. It will be 0 because there is no connectivity. So diagonal we will have based on the self loop. Others, this entry is 0, 1. This means 2. 0, 2. 0, 2, I have 5. 0, 3, not available. 3 to 0 is there, but 0, 3 is not. 0 to 4, not available. 1, 0. 1, 0, not available. So here I have 2, but here this is 1. 1, 2. 1 to 2, not available. 2 to 1 is available, but this will be 0. 1 to 3, yes, available. Sorry, 1 to 3, not available. 1 to 4, 3. 2 to 0. 2 to 0, I have this 2 to 0, not available. 2 to 1. 2 to 1, yes, 4 available. 2 to 3. 2 to 3, not available. 2 to 4, not available. Like this. So this becomes your directed graph storage. Of course, you can say if you have n vertices, n square space needed always. Whether edges are less or more, space needed will be always n square. And then you can accordingly have various logics and algos based on this. You know this information, from here, every information. For example, I want to say, I want to go to from vertex 0 to vertex 4. Then I will say I can go 0 to 1, 1 to 4. I can go 0 to 2, 2 to 4. I can go 0 to 3, 3 to 2, 2 to 4. I can go 0 to 3, 0 to 2, 2 to 1, 1 to 4. So many paths exist, and I have to find all paths. Path mean effectively sequence of edges. So in the graph, there will be many paths possible between vertex 0 to vertex 4, let's say. Which one is the shortest? So I have to make algo for that. So there are lots of algos which you are going to study in the next semester, and you will be solving many such problems like this. So all that you will be studying in detail, but ultimately you have to develop and understand some standard logics and some new algorithms. This is one storage. The other storage is linked list storage. That will be effectively via adjacency list. So adjacency list representation means that it is linked list based. So linked list for adjacents of every vertex. Effectively, that means this. Meaning that now I will have array of pointers for vertex 0. This is one linked list. Linked list of adjacent nodes or adjacent vertices of vertex 0. And similarly for vertex 1, similarly for vertex n minus 1. So there are effectively n linked lists. I'll say n linked lists being maintained. Initially, of course, we will talk of these being singly linked lists. And of course, if needed, they can be doubly also. By default, they will be considered to be singly linked lists. So n linked lists will exist in this particular situation. Now, knowing this, you are going to use this for linked list processing. For example, if I say I have a graph, directed graph, which is the same as this graph. So corresponding to the same this adjacent graph, this directed graph, let's say this one, I will make its adjacency list representation. So I will say for vertex 0, I have vertex 1, its adjacent. So vertex number, its a weight also if needed being stored. So 1, 2, and then next. So 1 is adjacent, 2 is also adjacent, vertex 2 adjacent. No, vertex 0 to 2 with weight 5. If there is any more adjacent, no. So I'll have this further null. This becomes for the vertex 0. Similarly, for the vertex 1 is this vertex. It has only one outgoing edge, is vertex 4, weight 3, and null. Vertex 2, is there any vertex 2's outgoing edge? Yes, 2 to 1. So it is going to vertex 1 with weight 4 and rest being null. And similarly for others. Again, unordered, so there is no guarantee that they will be sorted way of the edges. And first, initially, we will have vertex 1, then only vertex 2, not necessary. For example, if I have some vertex 6, for vertex 6, one adjacent node could be, let's say, vertex 2. Another adjacent node could be vertex 1. Another adjacent could be vertex number, say, 8. Another vertex adjacent could be, let's say, vertex number 3, unordered. There is no need that they will be ordered. Of course, corresponding weight will also be stored, etc., etc. So, unordered, the advantage of unordered is that insertion at the start will be very fast. Insertion at the start will be possible in order of 1 Ordered will mean you have to look for the corresponding place and then insertion becomes slow. So unordered has its own advantage, but yes, if you wanted faster algorithm based on some sorted values, of course, then sorting also can be used. So by default, it is unordered. But if you want a special logic, of course, you can make that. So this is called your adjacency list representation. If it was undirected graph will mean that if entry 1, 0, let's say no edge 1, 2 exists, this also means edge 2, 1 also by default. In undirected, but directed obviously not. So in indirected, if there is a connectivity from 4 to 1 also, then you could have, let's say, like this. So 1 to 4, there is one different weight. And this could be, let's say, -8. It's not same as -3. It could be a different weight. So if I have a directed graph and I want to show connection 1 to 4, it will be shown with arrow this. If I want to show connection from 4 to 1, I will have a separate edge showing the corresponding weight and connection. So all that will be used. So knowing this, now I can say that the storage is understood, then comes operations. So as far as their operations are concerned, again, the starting operation is always a traversal. So traversal in case of a graph is again two ways. One we call as a depth first traversal. And like in binary trees also we have discussed in order, pre-order, and another is called as breadth first. Very similar to binary trees. In case of a traversal, it is called as a DFS traversal for graphs, and this is called as a BFS traversal. Here S stands for search. This is called as a depth first search. This is a breadth first search. In fact, they are searching algos as well as a traversal usage, because a traversal and searching in graphs is closely connected to each other. So their traversal is effectively a kind of a search-based processing. So we call them as a DFS traversal or BFS traversal. As the word suggests, depth first. Depth first means go, let's say, have a start. So in both these cases, starting node is not fixed. So we will be choosing a starting node first of all. Anyone can be chosen as a starting node because there is no root like binary tree. Here, for example, for a particular graph, I could have, let's say, vertex 2 as a starting. No need that vertex 0 will be always taken. So depth first will mean that 2's first adjacent to be traversed, and from that adjacent, its first adjacent, and from there again its first adjacent, and so on. So whether it is your storage is array or linked list, if I have, let's say, graph 0 connected with 1, connected with 2, connected like this 3, connected 4, connected 5, and let's assume there are some directions also. Something like this. Let's say I started from 2. So 2 will be traversed first. Down. Now from 2, it has many adjacents. Like 1 is also there, 3 is also there, 5 is also there, 6 is also there. In the order of storage in your adjacency list, whichever is stored first, we will go there. With adjacency matrix, obviously, the first one will reach there. But let's say somehow we traversed using adjacency list and we went to any one, 3. So we will reach to 3. 3 will be traversed, but now remaining adjacents of 2 will not be traversed. First, I will traverse a 3's adjacent. So 3 has one adjacent 5. I will go to 5. 5 might have many adjacents, including 2 also. So I will say, okay, 5 has an adjacent 2, but 2 is already traversed, not traversed again. 2's, 5's any other traversal. Let's say 3 is again traversed, to be traversed. 3 is also adjacent, but 3 is also already traversed. Nothing to be done. 5 is over now. 5 is over. We will resume at the previous 3. 3 is adjacent. No other adjacent available. So 3 is also over. Go to 2. From 2, it comes to know, okay, I will go to 1. From 2, let's say I go to 1 now. So 1 reached. From 1, then I will say now it's adjacents to be traversed. 2's remaining come later. 1 to 4. 4 to 3 already traversed. Don't go. 4 has no more. Resume at 1. Maybe 1 has adjacent like this. So I'll say from 1, I will go to 6. 6 adjacent to be traversed. 5 already traversed. 6 adjacent to 0 traversed. 0's adjacent to be traversed now. 1 already traversed. 0 over. 0 over means resume at 6. 6 over. Resume at 4. 4 is already over. Very probably earlier. Similarly, then we'll say I'll reach to 2. All traversed. Not only that, there could be some node like here 8, which could be collected like here 9. There could be another 7. There could be another 10. So if I have traversed some and there are some untraversed vertices, so I'll have a list which has been traversed, which has not been traversed. Once all traversals, all recursion over and still there are untraversed, I will say 0 to 6 have been traversed, go to 7th then. I will check one by one all and maybe 7 started. 7's adjacent, let's say 10. 10's adjacent, nothing. 7's more adjacent, nothing. After that, I will say again, some more left? Yes, 8's. Maybe 8 has a connection like this. 8 traverse, but 8 has no adjacent. Some more left? Yes, 9 left. I will go to 9. So my DFS traversal will work like this. On the other hand, BFS means, say, from 2, all adjacents of 2. And then all them to be further. So 2's adjacent. 2's adjacent, like initially I said 3 was the first. So 3 will be traversed. But after 3, I won't jump to 3. I will say after 2, after 3, 2 has one more adjacent. Let's say 1. 2 has one more adjacent. Let's say 5. 2 has one more adjacent. Let's say 6. So 3, 1, 5, 6. From 2 we started. All 3 traversed. And then once all 2's adjacents are over, then I will say 3 is adjacent. 3 is adjacent. 5 is already covered. 3 is adjacent. Nobody else. 1's adjacent. 1's adjacent 6 is already covered. 1's adjacent 4. So 4 will be covered now. Then 4, then 5's adjacent. All covered. 6 adjacent. Say 0 will be covered. And like this. All covered. Some are totally untraversed at all. So I will go to, let's say, 7. 7's all adjacent to be covered. Then 10's adjacent, if any. Similarly, 8 and 8's adjacent. Then 9 and 9 adjacent. So the wording is very similar to what we have done in case of a tree. Depth first means whatever node we started, from this node, we will go to some node. From there, whatever its any selection we picked, then we will go to its adjacents, its adjacents, its adjacents, and so and so. So the ordering is the depth based. Effectively meaning that we are going down, 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 down. So whether you show anywhere, it is depth wise. Breadth first mean all breadth wise covered. If I am on this node, this has this connectivity, this has this connectivity, this has this connectivity, all to be traversed. Effectively considering this as this is node 2, it has got certain downwards multiple nodes. All these are breadth-wise, all these to be traversed. Then they further to be traversed. Even if they are going downwards, upwards, now all those links are possible, but we symbolically consider like this. So this is going to be breadth first traverse. So tree versus graph, you can see there is a significant difference. Both are non-linear data structures, but in tree, in binary tree or in tree always, in fact, in tree, I will say, each node has only, or I will say exactly one incoming node, exactly one incoming connection, incoming edge, which will come from parent actually. And each node means except root. Root has no incoming edge, but all other nodes have only and exactly one incoming edge. In graph, many incoming edges are possible. Hence, there is no hierarchical relation, and graph don't say hierarchical storage, and here many incoming edges are possible. So we can easily say each tree is a graph, because tree also means set of vertices and set of edges. So each tree is a graph guaranteedly, but vice versa is not true. Reverse might not be true, because each graph might not be a tree, because the tree needs only for each node only one children, only one parent to exist. So tree and graph have a lot of connectivity. In a tree also, you discussed depth first traversal using in order, pre-order, post-order. In breadth first, effectively you have done the level order. So more or less whatever you have studied there, the similar concepts are applicable in graphs also. So I will say for good students, now it's a good time to practice store a graph as adjacency matrix or adjacency list. Convert from one to the other and implement DFS, BFS. Both you can do using first adjacency list, which will be much more easier as we have discussed. But you can also do the same using adjacency matrix. So the good students must try to do these programming. Of course, next semester you are going to do all this, and along with many other new algos will you study in next semester. There are lots of useful algorithms which are applicable for the graphs, and they are used in real life situations like LinkedIn, Facebook, all these Google, and all Google Maps, etc. Everyone uses lots of such algos with various changes and permutations and combinations. With this, I think it's the right time to stop, and wishing you a great success in your life, as well as a very good attempt of your examination papers for data structures along with all other subjects. Prepare well, do a lot of practice on programming, and I'm sure you will enjoy the data structures and other continued programs or other subjects related to this in longer run. Bye-bye. All the best to all of you.